Okay, now this is question 6, and we have a different system here. In A, we will look for the stabilizing interval, as usual. And in B, we will look for the first order Faddy approximation, and the stability interval for that, and then also for the second, and see and then compare all the stuff. So we have a more basic and a much simpler system. And well, first of all, for this system, we will use again the body plot. And if you have the body plot for the whole system here, then the argument, so for A, the argument of, let's call it 10 e to the power of minus s divided by s plus 10 should be equal to minus 180 degrees. This happens at 2.86 radians per second. We look for the magnitude, then the inverse of that, that gives us basically 1 divided by 0.9614, which is 104 approximately. So 0K104. This is just for comparison. So this is the body plot version, which is basically the most correct version that we can use. Because if you remember this, if you have a system with delay, and if you want to look for the stability interval using the time domain, it becomes a bit of a problem because we don't really have a closed loop that is suitable for us. And by that I mean the following. If we have kgs divided by 1 plus k times gs, this is basically 10k e to the power of minus s divided by s plus 10 divided by 1 plus 10k e to the power of minus s divided by s plus 10. And this results in 10k e to the power of minus s plus 10 plus 10 to the power of 10 times k e to the power of minus s. Now, if you want to look for the stability interval of such a closed loop, the problem is that the characteristic polynomial, or the denominator, is not really a polynomial. Therefore, we cannot look for its poles, look for the stability interval as usual, because we have e to the power of minus s, which causes some problems. Therefore, we cannot use the polynomial methods that we know of. So therefore, we don't really have choice, because we can use the frequency method here. That gives us directly the interval. Pretty nice. But for the time domain, we cannot compare it with anything, because we don't really have the tool for it. But an idea might be to use the first order and second order Faddy approximation, because that will give us basically a system that's workable on. And then we can maybe look for the stability interval. So let's try that. Now for the first order Faddy approximation, for B, for the first order Faddy approximation, we have e to the power of minus tau s, 0.5, minus 0.5 tau s plus 1, 0.5 tau s plus 1. So we can see that we have a pole here, we have a zero here, a pole here, this is symmetric, basically, so 2 tau and minus 2 tau. Is that correct? I can say this. Or 1 divided by 2 tau. Tau, 2 tau. I guess this is correct. So this is kind of the structure that we replace e to the power of minus s with. Therefore, we'll get the approximate closed loop that would look like the following. So we have 10k and then 0.5 tau s plus 1 divided by 0.5 tau s plus 1 divided by s plus 10 plus 10 k 0.5 tau s plus 1, 0.5 tau s plus 1. Of course, tau is 1, so 0.5. Yeah. Now, the closed loop, if we work off this whole thing with tau equals 1, what we get is the following: minus 10k s plus 20k divided by s squared plus 12 minus 10k s 20 plus 20k. This is basically the closed loop. And we only have k as an unknown, as usual. Therefore, we can use s equals j omega on this, equate it to 0, look for the stability interval. So that's basically what we can do here. So s equals j omega, we'll get the following. We'll get minus omega squared, I guess, and then plus 12 minus 10k j omega plus 20 plus 20k equals 0. Therefore, we'll combine the real part and the imaginary parts. They should be equal to 0. So minus omega squared, and this gives us, or I have the inverse here, omega squared minus 20k, minus 20 should be equal to 0, and 10k minus 12 should be equal to 0, I guess. So we can see that k should be 1.2 here, and if you plug in that, we'll also get the frequency here. So omega squared is 20k, so 24, I guess 44 should be the result. So we get the frequency, which is 6.6, so omega is 6.6 roughly, and k is 1.2. So that's if we use the first order Buddy approximation. Now you can see that the actual stability interval does not include this value of 1.2. So this is not really the value that we are looking for, because it's not in the stability interval. So it seems like the Buddy approximation, this approximated system, has a stability interval of 1.2. But this doesn't mean that the actual system has the same stability interval. Because there is an approximation, we lose information there. This approximation should work so good that this should also be valid for the actual system with delay, but it's not. But what we can tell is that for greater values than 1.2, the approximation is not stable. Therefore, the actual system is also not stable. The only conclusion that we can come to is basically this. If it's greater than 1.2, it's not stable. But is it really stable between 0 and 1.2? We are not really sure. The approximation is, but the actual system may not be. So there's a huge difference. And even though if we increase the approximation order, so let me just take this part here. If we use a better approximation, we'll see e to the power of minus s is equal to, I guess, s squared divided by 12 minus s divided by 2 plus 1 divided by s squared plus s plus 1. Even if we take this approximation, I hope that it is correct, which is, by the way, converted into s squared minus, if we multiply with 12, we get 6s plus 12, s squared plus 6s plus 12. which corresponds to basically these poles and zeros. Even if we take this approximation, our end result, I'm not going to go through all the details, 120k minus 10k omega squared plus 120 is equal to 0, which will then give 72 omega minus 60k omega minus omega cubed is equal to 0. So omega 0 is again one solution, and the other one is the second order polynomial. You can solve that. And you'll get omega equals 3.046, and the k value, corresponding k value is 1.0454. So now this approximation looks a little bit better. It has better performance, but still there's this part 54 which is not included in the actual stability interval, but of course the digits are improving and it's becoming more accurate as we increase the order of the Pali approximation. But here, in fewer steps, in a high accuracy, we don't really need to use any Pali approximation. We can just work out what the actual stability interval is, because again, this does not guarantee that the actual system is stable, but it ends up in 454 not stable. So we can see that we are narrowing down the stability interval. At least we are sure of the instability interval, but we cannot really conclude what the stability interval of the actual system with delay is. But we can approximate or find the upper bound to it, but again, it doesn't have to apply to the actual system, because this approximation is just used for design purposes, not stability analysis. I would not prefer to use the Pali approximation for stability analysis, because the results are not really helping us. They're just giving us some upper bounds. But I can also go ahead and try to come up with a k value that is stable or not by just using trial and error. So it's not really that useful in this sense. But if I'm trying to design a controller, API controller for a certain settling time and overshoot, then this becomes handy. But for stability interval or analysis, I just use the body method here. So that's basically Q6.